The majority of Earth scientists accept plate tectonics and seafloor spreading as the best framework into which the multitude of geological and geophysical data can be fitted. And indeed now, some 15 years after the introduction of the theory, no serious objections to plate tectonics have been raised. But seafloor spreading means that continents now separated by wide oceans were once one. And one of the remaining and fascinating geological problems is not how the seafloor spreads, but how and why continental plates split to form new ocean basins. The fit here of South America to Africa is excellent, and there can be little doubt that less than 200 million years ago there was an Afro-American supercontinent. Why did it split up here? Why didn't it split up the Benue Trough and across Algeria, where there are known major fault systems? And the simple answer is, we don't know. The geological evidence that might be preserved in the oldest parts of the oceans has been covered by sediments. And what evidence there was on land has been subjected to 200 million years of weathering and erosion. So if we can't explain why the South Atlantic, one of our most recent ocean basins, why it formed, what hope is there of deducing how and why continental split? Now fortunately, we have a still younger ocean here, the Red Sea. And here we have a transcontinental split between Africa and Arabia that's occurred in the very recent geological past. And we know there's an active constructive margin down the axis of the Red Sea. So if we're going to answer the questions of how and why do continents split, then this is the place to investigate the problem. Of course, what you notice straight away is the parallelism of the coastlines. Note here in the north that the coastlines are straight, continuing the line of the Gulf of Suez. And then they start to zigzag, but together, until at the southern extremity, Africa and Arabia are only about 50 kilometers apart. When you fit Arabia back to Africa, Arabia has to be moved southwestwards, and over most of its length, the coastline fit is excellent. Obviously, there's been a lot of transcurrent movement here in the Gulf of Aqaba, and we have problems of overlap here in the north, and even more so down here in the south. But the fit is so good that you intuitively feel that there must be something in the proposal that in geological time there was until recently one continent. And if there was one continent, is there or was there something about that continent that made it especially prone to splitting? And the answer seemingly is no. Geophysically, it is a typical piece of continental plate with some 35 kilometers of sealic crust consisting of granitic and metamorphic rocks overlying peridotite upper mantle. The crust, which we often call the basement, is not particularly old. It was formed sometime between 1200 and 500 million years ago. During the Phanerozoic, the last 540 million years, nothing much has happened. The continental plate had formed and was moving over the Earth in response to several phases of seafloor spreading, and on the way it collected a sedimentary veneer that in turn has been largely removed by erosion. There were no major tectonic or magmatic episodes. Then quite suddenly, about 30 million years ago, basalt started to pour out over the southern area on top of an eroded surface. And some 10 million years later, all this area had been covered by lavas in places to a depth of 3 kilometers. But there was something else going on at this time. Look at this outcrop of basement. And these escarpments. This erosion surface was formed at near sea level, but it's since been raised by nearly 2 kilometers above sea level. The whole region has been updomed, mostly around here. And one possibility to explain the initial formation of the Red Sea is that this bulging of the crust caused stretching across the line of the Red Sea and the development of a trough or graben. or perhaps the two plates moved apart before the uplift happened, or perhaps there are elements of both processes. But one way of tackling this problem is to look at the sediments. For the history of any stretch of water, the Red Sea included, is recorded in the sediments that are deposited there. Peter.
During the last 20 million years, this area has certainly been one of considerable instability. But prior to that, for 500 million years, this was a very stable area. During that period of stability, terrestrial sediments were deposited over the whole of the area. These terrestrial sediments were interbedded with marine and intertidal sediments, which were the result of transgressions coming up from the north in this direction here. These terrestrial sediments are very similar to the millstone grit in Britain. Unlike the millstone grit, they are a facies deposit. That is, they vary in age from place to place. These deposits are called the Nubian and were laid down in large, flat, depositional sheets of fairly coarse sediment. This scarp is in Libya, and similar deposits can be found as far east as Jordan. Just look at these structures, which can be found throughout these deposits. Detailed mapping of them showed that they're deposits of a large braided river. These conditions must have lasted a long time, because these similar sediments are known to be lower Paleozoic in age. So we're sure that rivers must have been draining this area here for hundreds of millions of years. These braided rivers flowed from an upland region in the south here, northward into an ocean up here. During the Lower Cretaceous, a marine transgression covered the whole of this area here, depositing over Sinai limestones. Further south, towards the coastline, we find shale deposits. The best exposed outcrop is found at Quasir, and these shales, with plant remains, are interbedded with shallow water limestones rich in oysters and with phosphates. This is a clear indication that the coastline must have been fluctuating in this area here. Limestones continued to be deposited during the Lower and Middle Eocene, and these sediments stretched from the Tigris-Euphrates Valley in the east right the way across this area here and down into western Egypt. These rocks are a mixture of chalks and bioclastic limestones, suggesting a shallow water, high energy environment, similar in fact to the Florida Keys today. And in the past, these limestones have proved to be quite a durable building stone. Up to the Middle Eocene, 45 million years ago, it's important to remember that none of these deposits showed any change in facies. All that happened was that the coastline migrated up and down. Towards the end of the Eocene, a major regression occurred and left the coastline in northern Sinai. This was followed by a dramatic change in pattern of sedimentation. Coarse conglomerates like this are found throughout much of the Red Sea area, and they were formed in Piedmont fans. It's difficult to date them, but fossils have been found in marine sediments above and associated with the conglomerates, suggesting that they were formed during the Lower Oligocene, some 30 million years ago. These Piedmont fans were formed as a result of uplift of the margins of the incipient Red Sea, along here. And this is the first sedimentary evidence of anything strange happening in this area. What's more, the trend of sedimentation along the line of the present Red Sea instead of along the old coastline. As we move into the Miocene, the flanks continued to rise, and a marine trough formed in between, open to the north but closed to the south. Once sedimentation has been established, a definite pattern emerged. And in order to understand the Miocene sedimentation properly, we need to look in detail at a cross-section along here. This is the section, and unlike the rest of the Red Sea, the Gulf of Suez is a graben, and you can clearly see the marginal faults in the cross-section. let's have a look in detail at one area here. This represents a typical sequence anywhere in the Gulf of Suez. The section from top to bottom represents about 4,000 meters. As you can see, the basement crystalline rocks here have been faulted into a horst. Both the Nubian sandstone here and the later chalks and limestones were deposited before the faulting and were therefore unaffected by it. We simply find the same sequence lifted up here on the horst. The last deposits laid down before faulting are these upper Eocene chalks, here and here. These are about 40 million years old. All these younger deposits, from the Oligocene gravels upwards, have been draped over the topography produced by the faulting. Here we have a shallow water reef of Miocene age, whereas away from the horst you find shales of similar age, suggesting deep water. Within the Miocene we find evaporites of several types, anhydrites here and halite here. These indicate periods of lower sea level and considerable aridity, which must have resulted from the Red Sea having been cut off from the world's oceans. The reason why we know so much about this region is because of these. These are the source rocks for the oil found in the area, and of course the oil companies have widely drilled in this area and logged the rocks in considerable detail. These oil-rich rocks were probably deposited in relatively deep water of normal salinity and considerable organic activity. The contrast between the evaporites and the oil shales indicates considerable changes in sea levels. Now there is more evidence of these fluctuations to be found in the sediments further south in the Red Sea proper. During high stands of sea level in the Miocene, conglomerate fans and shallow water reefs were being formed along the margins of the Red Sea, and in deeper water, shales containing planktonic organisms were being deposited. All these features indicate a sea of normal salinity. For a number of reasons, the Red Sea must have been cut off at some time, and as the sea became isolated, evaporation caused sea level to fall. Salinity increased to about 10 times what it is normally, and halite was deposited. Each time this happened, a little less than 2 meters halite was laid down. But we find thin shale bands interbedded with the halite, so sea level must have risen again periodically. We know there's a total thickness of 5 kilometers of halite in the Red Sea basin at the present time. This means that the process of filling and evaporation must have been repeated nearly 300 times. This process ended in the Pliocene, 5 million years ago, when the southern end of the Red Sea opened to the Indian Ocean, and shales with an Indian Ocean fauna were deposited over the whole of this area. This process continues to the present day.
Well, if Africa and Arabia were one until, say, 20 million years ago, as the sediments indicate, and if the coastline fit is still the best bet, we still have two problems, both involving coastline overlap. The biggest overlap is here in the southern area, and it's the Afar Triangle. But this area is known to consist largely of recent basalts erupted within the last 20 million years, so they can be ignored in any 20 million year reconstruction. There is a minor complication, however, and it's this ridge of high ground, the Danakil Alps. These mountains are underlain by basement rocks. How and why they are there, surrounded by basaltic lava flows, is a problem. The tectonic situation in the area where these three plates join is complex. There hasn't been much movement between the Nubian and the Somali plates, but when Arabia started to move away from Africa, a fragment of the African basement seems to have got torn off in the spreading process, and as it wasn't attached to Arabia, it was left behind, stranded as a fragment of crust, a microplate. But note that as the Arabian plate moves relative to the African plate, both the Red Sea and the Gulf of Aden are formed together. So it would seem that at the southern end of the Red Sea, if we dispose of the Afar triangle, the coastal fit is good. But the northern end of the Red Sea still presents problems. Movement must have occurred here along the Aqaba transform. And this area, the Midian Peninsula, upsets the good coastal fit. This is obviously another complication. And to understand this area, we need someone who knows the region well. Doug?
Well, here we are. We've moved some 1,200 kilometers north up to the head of the Red Sea, where it bifurcates into the Gulf of Suez and the Gulf of Aqaba. Now, these two are quite different from one another. The Gulf of Suez continues the trend of the Red Sea, but unlike the Red Sea, it is very shallow. It is nowhere deeper than 200 meters. Geologically, it is a graben structure, and on the satellite image, we can see the boundary escarpments on either side quite clearly, here on Sinai and here on the African side. Also, we can see the horse blocks within the graben, one there, another there, and another there. The region is an oil-producing one, and there are wells not only onshore, but also offshore in the Gulf here. And all the information gained from oil field exploration has gone to demonstrate that the graben is underlain by continental crust. This means that the Gulf of Suez cannot have opened by seafloor spreading. That is, not by the generation of new crust along its axis. There must, of course, have been some extension across the region to allow the graben blocks to fall, but that extension can only amount to quite a small part of the present width. Now, this information is quite important because it does mean that in any reconstructions that we make of the evolution of the opening of the Red Sea, in none of those reconstructions can we close the Gulf of Suez. The Gulf of Aqaba is relatively narrow, it's steep-sided, and quite deep. Locally, it achieves depths of 16 to 1,700 meters. Now, this line is a line of a major fault, and the Gemini astronauts were able to look along this fault, and fortunately, they photographed it for us. Here we see the trend of the Gulf of Aqaba, and then you can trace the fault all the way up Wadi Araba to the Dead Sea, and it continues beyond. The line of the fault is quite clear there. Now, the displacement on the fault is sinistral, that the rocks facing you have moved to the left, and we can demonstrate that here. Just here in the northeast corner of Sinai, there are outcrops of quartz porphyry. Similar quartz porphyries occur in Jordan on the other side of the fault, up here near Petra. The distance between the two along the line of the fault is 105 kilometers. Now, elsewhere along the fault, we can demonstrate that the movement took place in two main phases. One, relatively recent, within the past 5 million years, of 40 to 45 kilometers, and the other, somewhat earlier, of 60 kilometers, the two together amounting to 105. Now, if the Red Sea opened by drift of Arabia away from Africa, then the separation can only have been achieved by movement along this line. It was the almost perfect match in the configuration of the opposing coastlines which first drew attention to the possibility that the present Red Sea was the result of the drift of Arabia away from Africa. However, bear in mind that we cannot close the Gulf of Suez. It is a graben underlain by continental crust. Here in the north, the fit is almost perfect, except for the small peninsula of Midian, which overlaps Africa. Although the peninsula mostly comprises late tertiary sediments, there are inliers of basement rocks, so it's partly at least continental crust, and it projects into the Shield of Africa where there is no re-entrant to accommodate it. These rocks lie immediately adjacent to the Aqaba Fault, and it's likely that they were originally parts of the Arabian Shield, which became displaced during movement along the fault. So we can discount them in this fit. We know that a sinistral movement of 105 kilometers has occurred along the Aqaba Jordan Valley Fault. The trouble is, such movement does not open the Red Sea to its present position. Something is obviously wrong. Perhaps our assumption of a tight coast-to-coast fit was in error. So let us start from a position about which we are certain, namely present-day geography. Move the Arabian Plate 105 kilometers back along the Aqaba Fault. This brings the northern coastline of Saudi Arabia into almost direct continuity with the boundary escarpment of the Suez Graben in Sinai, and it makes the northern sector of the Red Sea continuous with the present Gulf of Suez Graben. The implications could be that prior to the initiation of spreading, the northern part of the Red Sea was part and parcel of the Suez Graben. Well, here once again, the astronauts have given us a God's eye view looking down the Gulf of Suez into the northern part of the Red Sea. Had they been in space, say 20 million years ago, somewhere at the beginning of the Miocene, this is what they may have seen.
So neither of the problem areas have turned out to be much of a problem. And although Doug Sherman believes that the northern part, at least, started as a graben and needs some continental crust offshore, we still have a near-perfect coast-to-coast fit. We're also sure from the sedimentary evidence that the whole evolution of the Red Sea has occurred in the last 30 million years. Up until then, there was a low-lying landmass to the south around here, and rivers were draining northwards into broad, warm, shallow seas. Then, about 30 million years ago, basalts erupted all over this southern area, and they were erupted over a flat surface, and the area began to sag under their weight. Remember, there were about 3 kilometers of basalts in some areas. By 20 million years, all this activity had stopped, and a trough had begun to form along the line of the present-day Red Sea. The flanks had begun to rise, and rivers were draining into this linear depression. But at no time was the Red Sea region above sea level, because we find marine sediments deposited in the trough throughout the period. The ancient continent was beginning to split, with the Arabian Plate moving northwestwards away from Africa. To find out exactly how and why this split occurred, we need to look at the submarine geology beneath the Red Sea, and we'll be doing that in the second program of this case study.